This is section 2.2, fitting lines to data points, using them to model linear functions. In this section, we're going to do a lot with the calculator. We're going to talk more about linear models and linear regression and scatter plots, and we'll talk about other things you can analyze with those scatter plots. We're going to determine if linear models are approximate or exact, good fits, bad fits, and then we'll solve problems using those linear models. If you have not already printed the notes from the blank notes posted in Blackboard, I would highly suggest doing that before you continue this video. Most of the time it's not a big deal if you print them, but this particular lesson has a lot of charts and graphs and data things that would be pretty difficult to copy down by hand. So if you want to pause the video and print out the notes, it might be a good idea for today. Okay, the first thing that you're going to need to do in this lesson, and then we're going to circle back to this at the very end, is we're going to be doing an activity using our linear regression and our predictions and the things that we're going to discuss here. So what you need to do before you continue the video, and it will pause in a second to give you some time to do that, is you need to fill out L2 in this chart, and no cheating. You need to fill out your guess for the age of the following celebrities. And just to make it easy, let's just do nice, pretty whole numbers. We're not going to say somebody is 42 1/4 years old or anything. So the video is going to pause. I want you to either write these down in your notebook or fill out the chart if you've printed the notes out. Guess just in L2 how old you think each of these celebrities are. All right, so the first thing we're going to talk about are exact fits for linear functions. We can determine if data can be measured exactly with linear data by determining if the changes in the output are equal changes for equal values of changes in the input. In this case, we say that the inputs are uniform and therefore the first differences can be considered constant. So let me give you an example. When we're talking about inputs, we're talking about our x's or our first column or our independent variable. It can be listed a bunch of different ways, but we want to make sure that our inputs are uniform, meaning they're counting by the same number over and over again. So in this table, my time is my inputs or my independent variable. And you can see it's just increasing by 1 over and over again. So here we would say that the inputs are uniform. Now, if I went from 0 to 2, and then 2 to 5, and then 5 to 6, we would not have uniform inputs, and we would not be able to use this method to determine if we have a linear function that's exact fit. Then, if you feel like you have uniform inputs, you are going to look at the outputs. And we're going to find what we call the first differences in the outputs. To calculate first differences, you're going to take one data value minus the one before it. Okay, so in this case, that would be 39.2 minus 49. And you can use your calculator for any of these if you need to, especially if you get weird numbers. And you're going to get negative 9.8. And it makes sense. Oop, there's my decimal. It makes sense that we would have a negative here because you can see the data is decreasing as we go from 0 to 1 seconds in this example. Then we're going to do the same thing for the next pair. So we're going to do 29.4 minus 39.2. 29.4, you can just put in your calculator, minus 39.2, and I again get negative 9.8. Now, just because two of them are the same doesn't mean necessarily all of our data is going to be exact fit. We might have a data value that doesn't go along with the others. So we want to make sure we continue this all the way. So we're going to do 19.6 minus 29.4, also negative 9.8. 9.8 minus 19.6, also negative 9.8. And then 0 minus 9.8 is, of course, negative 9.8. So we say that, yes, this is an exact linear model. And then you could write the equation that goes along with this. So we're going to say we are going to use y equals mx plus b, like we've used before. That first difference that you're finding is your slope. It's what you're increasing by from one term to the next. And because our time was going up by 1, it's just negative 9.8 over 1, or negative 9.8. The other thing you need to write an equation in slope-intercept form is a y-intercept. Remember, a y-intercept b is when x equals 0. And we actually have that in our table here. We had, when our time was 0, the speed was 49. So plus 49. And then there's your exact linear model to represent this data. Now, if you did what we've done in the calculator before, put all this data in, stat, calculate, linear regression, you would say you get exactly the same answer there. So sometimes it's nice, and we're going to be able to calculate these by hand. Some sets of data are approximate fits or nonlinear fits. So let's look at the one on the left here. It says if first differences are nearly constant, so close to the same number over and over again, but not necessarily exactly the same every time, we say that if they're nearly constant, we can still use a linear function to model it, but it's only an approximate model versus an exact model, so it's an estimation. So let's look at first differences in this example. And again, we're just going to subtract, so 18.9 minus 15.7 gives me 3.2. 21.1 minus 18.9 gives me 2.2. 24.2 minus 21.1 gives me 3.1. 27.2 minus 24.2 gives me 3.0. 29 minus 27.2 gives me 1.8. 31.4 minus 29 gives me 2.4. 32.1 minus 31.4 gives me 0.7. And then finally, 34.2 minus 32.1 gives me 2.1. So you can see we definitely don't have constant first differences in this problem, but they're similar. They're all increasing from one term to the next. And by the way, notice we didn't discuss this at the beginning here, but we do have that uniform differences in all of my x's. We're going up by 5 from one term to the next. So we would say that this is nearly constant, and you could use a linear function to represent it. Now, if you have an approximate fit, like this example, this is where you would use the calculator then to do the line of regression instead of trying to do it by hand, because we don't have an exact slope for any of these. Finally, it is possible that you have just a nonlinear function. So you have a set of data that really can't be modeled with a line. If the first differences are either not constant or not even nearly constant, we say we have a nonlinear function, which means if I were to connect all of this data together, it wouldn't even look like a trend in a line. And we'll talk about what that looks like a little bit more in this lesson. So let's look at some of these here. Again, we'll look at those first differences. And notice here my time, my inputs, they're all going up by 10. So again, I have uniform inputs. I'm going to start with 146.5 minus 172. That gives me negative 25.5. 131.2 minus 146.5 gives me negative 15.3. 116.3 minus 131.2 gives me negative 14.9. 110, 0.5 minus 116.3, negative 5.8. 104.4 minus 110.5, negative 6.1. And then finally 99.9 minus 104.4, negative 4.5. So you can see here my first differences do have something in common. The differences are getting smaller and smaller and smaller each time, or close to that trend, but definitely not anything that's constant or a nearly constant number. Everything in the example on the left was between 0.7 and 3.2. We had a range of numbers that all of our differences were falling between. This one on the right is all over the place. So we say that this is a non-linear function. Okay, I want you guys to practice these on your own. In each table below, I want you to determine if it is an exact, let me underline it here, exact linear approximate linear, or nonlinear. And you're going to do that by finding the first differences each time. From there, then, whichever one is exact, if you have any or multiple that are exact linear functions, I want you to find the equation of the line using the slope, which is your first differences, and your y-intercept, which is the value when x equals 0, when your input equals 0. Okay, go ahead and try these on your own. All right, number 1, first differences are 2, 3, 6, 4, 3. Number 2, our first differences are 60, 150, negative 75, 150, negative 115, negative 45, negative 50, what's that one? I can't do that in my head. 191, negative 64. There we go. And then the last one, 123 minus 191, negative 68. First differences for the last one, 3, 3, 3, 3, 3, 3. All right, so if you're looking for the one that is exact linear, that's number 3. Those are all the exact same set of first differences. Then we want something that's approximate. Number 1 is approximate linear. They're all similar type of values, but not the same number consistently. And then finally, number 2 is your non-linear example. Some are positive, some are negative, and these numbers are very, very different as we're going through. So now number 3, you should have written an equation in slope-intercept form, y equals mx plus b. Your slope is 3, and your y-intercept, again, is when your x equals 0, so that is 2. Y equals 3x plus 2 is your final answer for that equation, that linear function that represents that data. Okay, moving on, the next thing that's in this lesson is discrete versus continuous functions. We've got 2 definitions here. A discrete function can be represented with a finite number of inputs. So when we say finite number of inputs, that means that there is space between our data values. So for example, let's say my data was years, 1981, 1982, 1983. There's no years between 1981, 1982, 1983. So that would be an example of a discrete set of data because years are distinct values and we don't have values that fall between them. The other type of example would be a continuous function. This can be represented with an infinite number of inputs, and if you're looking on a graph to determine if a continuous function is continuous or not, it means you can trace the whole graph without picking up your pencil. So on the bottom here, you can see a couple examples on the left that are graphs of discrete versus continuous functions. Sometimes discrete, they'll make it into a line graph, something like this maybe. But if you see these distinct points, you have a discrete graph. If you have no distinct points, something like this little curve at the bottom, we say that that's a continuous graph. An example of a continuous graph would be the temperature of water as it boils. That's something that is continually changing. If I have something between 1 and 2 seconds, I can measure that 1.5 seconds, 1.25 seconds. The time is continuous and the temperature is continuous. So that's an example of something that we would measure with a continuous function. So let's talk about the ones at the bottom here, these tables. We want to know, would these tables, if we graph them, be represented with either discrete or continuous functions? We want to think about, would these data values have something between them or not? So here we have months, and we have the temperature, the average temperature for that month, and we have the average precipitation for that month. So what you would actually be graphing here are temperature would be your inputs, and precipitation would be your outputs. If these are average temperatures and total or average precipitation for these months in whatever location we're talking about here, we wouldn't have values between them. We wouldn't have an average temperature between January and February because we're just measuring each month. So we would say that this is a discrete set of data. We would only have these 12 points. If we look at the next one, this is an example of a diver's set of data. It's the depth that the diver is diving and then the water pressure around them. So if they're at 0 feet, if they're right at the surface, it's 14.7 pounds per square inch. And then if they go down 10 feet, it's 19.03 pounds per square inch. So the question is, would there be data values between 0 and 10? Absolutely. At some point, they're 1 foot, 2 foot, 3 foot, 4 foot, but even more than that, they can be a tenth of a foot or an inch or a millimeter. So there's all these values that fall between those feet measurements as well as the pressure. The pressure is continually changing. At some point, they're 14.701 and 14.702, and then we can make the decimals smaller and smaller, but that value is something that would continuously be increasing. And at any point in time, at any depth, we would be able to find a measurement for the pressure. So we say that this is continuous. So this tells us if we're actually graphing this, the first table of values could be represented with a scatter plot or a line graph. The second table or set of values would be represented with a smooth curve. All right, the next thing we're going to talk about is creating linear models by hand. And we have a set of data here to help us. We want to construct a scatter plot by hand, sketch a line of best fit, and then we're going to use a couple points that we find from our data to help us find an approximate linear model. So if you haven't printed this out already, you need to make a grid. These are all positive numbers, so we're staying in quadrant 1 of our axes, and we're just going to plot our points. So 2, 5, 2 to the right, 5 up, 5, 9, 8, 13, 9, 15, 10, 16, 12, 19, and 20. Oh my goodness, what am I doing? That is not right. I don't know what I'm doing. Did I do that right? 12, 19. Oh yeah. 16. 20. There we go. Okay. Once you have all of your data modeled here, you can see this is not an exact linear model. I wouldn't be able to draw a line that touches every single point on here, but it's going to be close. In general, I could say this trend is a line. So the next thing we want to do is sketch a line of best fit. When you sketch a line of best fit, you want to make a line that shows, again, the general trend in your data, and if it can't go through all of your data points, you want to try to make it so the same number of data values are above and below the line. So I'm going to see if I can get an approximate line. These are not going to be perfect. It's all just a rough sketch. Maybe something like that. Okay, so you can see I have a few points below, I have a few points above, and it's showing the general increase in the data. The next thing we want to do is we want to choose 2 points on our line, or as close to our line as we can get. So it looks like I have a point here that my line's going through and a point here that's my line's going through. And let's find out what those points are. That first one is 8, 13 from our table, and the other one was 16, 20 from our table. So I'm going to write that down. And now this is going to be review from Unit 1. If you have 2 points, you can find the equation of the line by first finding the slope, which is y2 minus y1 over x2 minus x1. So I'm going to get 7 over 8, and then that does not reduce. From there, to find the equation of the line, I'm going to use point slope form. Y minus y1 equals m, which I know that already, so I'm going to go ahead and fill it in, x minus x1. And you can use either of the points. I'm going to use the first point, so y minus 13 equals 7/8 times x minus 8. From there, I'm going to distribute my 7/8 through, which is going to give me 7/8 x minus 7. And then finally, we're going to add 13 to each side. So our final answer is y equals 7/8 x plus 6. And if we want to check if that's reasonable for what we've drawn here, you can see where I'm touching the x or y-axis is approximately at 6. So that's my y-intercept that we're seeing here in the graph. So that makes sense. And then if we wanted to check that that slope was appropriate, you could pick 2 points and calculate a rise and a run and see that approximately for every 7 units we go up, it's 8 units over. So again, reasonable for the picture that we're seeing there. So that's how you create a linear model by hand. Again, this linear model, if you have approximate data, is an approximate representation of the trend in the data. It's not perfect, but it does give us a general idea of what's happening with this data. Okay, so now we're going to get to some graphing calculator steps. We want to determine which of the following lines are a good fit to represent this data set. So here the data set is given to us as coordinates. You could always make it a table of x and y values. That's ultimately how you're going to put it in your calculator anyway. So all the x's are 20, 30, 40, 50, and 60. All my y's are 50, 73, 96, 119, and 142. So to do this, we're going to first review our steps in the graphing calculator for how to get a scatter plot. To do that, we're going to hit Stat, Edit, and we're going to clear out our lists that are in there. Go up to the list name, hit Clear, go back down. Up to the list name, hit Clear, go back down. Okay, my X's are 20, 30, 40, 50, and 60. My Y's are 50, 73, 96, 119, and 142. From there, if you want to see your scatter plot, we're going to go to y equals, and we're going to turn our plot on by going up to plot 1, hit enter, go back down. Then I'm going to hit zoom 9, which will zoom in on our statistics, and there we have our set of data, which looks, if it's not approximate linear, it may be exact linear even here. Now the problem was asking, we want to know which of the equations, A, B, or C on the left, are going to get a better fit for this data. And we can again use our calculator to help us here. In y equals, you can graph these equations. So 2.5x plus 2. Then I'll go down. I'm going to graph them all at once. It's nice in the color calculator because I'll know which one's which. I'm going to skip that one because it's not have a color. Let's like maybe go down to the green one. That way I have blue, red, and green. 2.1x plus 6. There we go. So I've got my first equation, it's going to graph in blue. My second equation, it's going to graph in red. And my third equation, it's going to graph in green. And so we'll be able to clearly see in this calculator which one then, based on the color of what I see, is going to represent the data the best. Now, if you have a black and white calculator, you may want to graph each of these one at a time. Or you can graph them all at once. You just have to be really kind of quick. As you notice, it's going to graph the first equation you put in first, the second equation you put in second, etc., etc. Okay, so blue, red, green were the order we put them in. Blue, red, green. And I think it's pretty obvious here. Red is obviously the best one. It's going to go through all of our data points, which that was this guy right here, 2.3x plus 4. And again, if you wanted to explain or represent that, you could easily make a rough sketch of this on a test or a quiz, or in MyMathLab, you could find the one that best represents this picture. Okay, the next thing we're going to talk about is interpolation versus extrapolation. The first definition is interpolation. That is when we estimate a value inside a set of data points. So let's say I have this set of data and it's already graphed in a scatter plot for us. It's temperature in degrees Celsius and the sales of something. Okay, and we have all of our data graphed. Anything that's a dot on here is an actual data point. If we wanted to estimate the sales at 21 degrees Celsius, 21 degrees Celsius falls between our data values. That makes it an interpolation problem. If you have an estimation that falls within data values that already exist, and that's how I remember it, it is in data values that already exist, it is interpolation. The other definition is extrapolation. That's when you're estimating a value outside of the data points. So here we have the same picture. I've got my temperatures in degrees Celsius. I have my sales, but in this example, they're estimating what the sales are when it's 29 degrees Celsius. And you can see that's past all of the data values that have already been collected. So we're still able to answer that question using our line of best fit, but we are extending the question and our data values beyond what we know to exist already. So interpolation is inside, extrapolation is outside. Good way to remember it. Next, we're going to talk about, if we're analyzing data, correlation coefficient. This is an R value, and we'll talk about the different values that R could be. Correlation in general shows the trend of the data. So you are said to have a positive correlation when your data is going up, everything's increasing. You are said to have a negative correlation when your values are decreasing. So if we look back at some of this data, maybe the last example we had our Celsius and our sales, we would say that this graph has a positive correlation because as my temperature increases, my sales increase. Okay, if we saw that line going down as the temperature went up, the sales went down, we would say that it has a negative correlation. We're going to calculate R with our calculator in a little bit here. The possible values of R range from +1 to -1. +1 represents a perfect positive correlation, which means that all your data values are on a line that goes up. If you have an R value of -1, it means all your data values are on a line that's going down. And I have pictures of those down here. So this is an example of a graph, the one on the bottom left here, that has a perfect positive correlation. Our data values are increasing from left to right, and they all make a line. We could draw one line that would represent this data and hit every single data value. And then on the far right, the other extreme, we have a perfect negative correlation. So again, I could draw one line that would touch all of these data values, but here my data is going down instead of up. So we would say that that has an R value of -1. Right in the middle of the two, we would say is an R value of 0, and 0 means no correlation, meaning we don't see any relationship between these data values. And you can see this kind of orange graph here. The data values are all over the place. There's no way to tell if I should make a horizontal line or a line going up or a line going down or a vertical line or anything that would really represent any trend in this data. So no correlation is represented with a 0. From there, we have a sliding scale. We could have an R value something like 0.9 or 0.8. We say that that's a strong positive correlation. It's not perfect, but our data values are clumped pretty close together, and again, they're increasing. This, something like a 0.5, 0.4, we say has a weak positive correlation. So again, our data values are still increasing, but they're definitely spread out a lot more. The same thing can happen if we have a weak negative or a strong negative. So weak negative, you're going to see an R value of something like negative 0.5, negative 0.4, negative 0.3, even negative 0.6. And if you look at your data, you're going to see it's spread out a little bit, but it's decreasing. If the data values get a little close together, we say it has a strong negative correlation. So something like negative 0.8, negative 0.9, that's strong. And again, if we get back to negative 1, we say it is perfect. The next thing we need to do is we need to turn on the correlation coefficient in your calculator because we're going to be calculating it in a moment. To do that, you're going to hit Mode. And in this calculator, we're looking towards the bottom where it says Stat Diagnostics. I'm going to scroll way down here. Oop, maybe. There we go. You can see right now my stat diagnostics are off because that's what's highlighted. If I go to the right and hit enter, it will turn my stat diagnostics on. So if you didn't have it on already, you want to make sure you turn it on. Everybody's calculator, that should be highlighted. If for some reason you have a really old version of the calculator and you don't see stat diagnostics here, you can go to second 0. That's our catalog. Then you can hit D. The letter D is 2 buttons below alpha. It's where it says matrix. And if you scroll down, down, you can hit enter to turn diagnostics on there as well. So that's another way to do it. That catalog is where you can find any function that's located in your calculator. So that's a great resource. If you feel like you can't find something in the calculator, you can find it in the catalog and still be able to use it. Okay, so either in mode, turn your diagnostics on, or in catalog, turn your diagnostics on. And then we're just going to hit second, quit, and go back to our home screen. Okay. So let's do this example. And we're going to use our calculators. We're going to create a linear model with the calculator. Here we have years and we have population in millions. For the years, you could type in 1960, 1965, 1970. Sometimes our numbers get a little big with that though. So I'm going to say instead of years, let's do years after 1900. So that means instead of 1960, I could just type in 60, 65, 70, if that makes sense. Gives me a little less I have to type in, and again, our numbers are going to be a little bit prettier in the calculator. All right, so let's get this in our calculator. We're going to hit, oop, don't do that. There we go. We're going to hit stat, go over to calculate, no, not yet. Stat edit, there we go. And we're going to go up, hit clear, go back down, up, hit clear, go back down. All right, L1, we're going to get all of our years. L2, we're going to get our population in millions. So 60, 65, 70, 75, 80, 85, 90, 95, 98. 2000 will actually be 100. 2003 will be 103. 2025 will be 125, 125 years after 1900, and 2050 will be 150. My L2s are all those populations. Okay, and then after you have all your data values in, Just make sure that you have the same number of values in L1 and L2. The first thing we want to do with this data is find a linear model to represent the data, and then we're going to interpret the slope and y-intercept. So we've done this before. We're going to hit Stat. We're going to go over to Calculate. We're going to select number 4, Linear Regression, and then we're just going to hit Enter a bunch of times. There we go. So we get a couple things here. Let me drag this over a little bit. I'm going to cover up my data slightly. So we have y equals ax plus b, and my a is my slope, and my b is my y-intercept. So my linear model is y equals, I'm going to give it 3 decimal places here, 2.60, if I round that, it's going to be 7, x plus 20.791. Okay, so from there, we're going to go ahead and find what our slope and our y-intercept represent. So let's start with the slope. The slope is 2.607. And remember, slope represents something that's constantly increasing or decreasing. So in this example, it means each year, because that's our x's, the population is going to increase because it's a positive number by 2.607, and remember this was measured in millions. Your y-intercept in real life represents an initial amount, a starting amount, or when x equals 0. Well, the way we set up our years here, x equals 0 was the year 1900, 0 years after 1900. So what we're seeing here is the y-intercept of 20.791 represents the population in the year 1900. And again, that population is also in millions, so 20 million was the population. Okay, next thing we're going to do is find the correlation coefficient and describe its meaning. Remember, correlation coefficient is an R, and because you turned on your stat diagnostics, you'll now see as part of this linear regression menu, you have an R value, 0.997. Now remember, R's range between -1 and +1. +1 is a perfect correlation. 0.997 is very, very close to that. So that tells us that this data has a strong positive correlation. I know it's positive because I have a positive number. If you had a negative number for R, you would have a negative correlation. We say strong because it's very close to 1. If we had a value that was exactly 1, we would say a perfect positive correlation. Next, we want to estimate the population in 2040. Now, our data went all the way up to 2050, so this is an example of interpolation. And we want to know what to plug in. Remember, our x's here represent years after 1900, so 2040 is 140 years after 2040. And we can use our calculator for this. I'm just going to hit second quit to go back to my home screen. 2.607 was my slope, times my x value here is 140 plus 20.791. So we would say the population in 2040 is about 385.771 million. Okay. The next thing we want to know, in what year will the population reach 450? To do this, we have to work backwards. Here we have a population, we have a y. So we're going to put that in for y in our equation. 2.607x plus 20.791. To solve for x, we're going to subtract 20.791 on each side, and I'm just going to do that on the calculator I have in my hand right now. So 450 minus 20.791 gives me 429.209 equals 2.607x. And then to solve for x, we're going to divide by 2.607. So I get 164.6 approximately. And remember again, that's years after 1900. So if we take 1900 and add about 165 years to it, we're going to say about 2065 is the year that we're going to reach that population. This is an example of estimating something with extrapolation. 2065 is a year that's beyond the data values that we were given. So we're estimating something well into the future here. Okay, so to wrap up the lesson today, we're going to go back now to the celebrity ages you put in that chart in the very first example. To be fair here, because I already knew the answers in L1, I had my husband guess for L2. So some of his guesses here are pretty entertaining, so I hope you enjoy them. So I want everybody to take a moment. I'm going to pause the video here in a second. I want you to fill out the rest of your table with these actual ages. This is as of yesterday, so this is recent data here. Hopefully nobody had a birthday. Don't call me out if they did have a birthday on September 19th. Take a second. I want you to get all of this data into your calculator, and then on the next slide we're going to find a line of regression with it and then answer a few more questions. Okay, I went ahead and got all the data in my calculator. Hopefully you have it in yours as well. First thing we're going to do is get our line of best fit, and then we'll be filling that out on the next page along with our correlation coefficient. So to get that line of best fit and correlation coefficient, it all happens at the same time now for us. We hit Stat. We're going to go over to Calculate, and then number 4, enter a bunch of times. And there is the equation for my husband's guesses. Now your numbers may look a little bit different here. So he has a slope of 0.883. So let's fill that in. Y equals 0.883x plus a y-intercept of 4.725. And whatever yours looks like, hopefully you're going to round that to 3 decimal places. You have a positive correlation probably happening with this. If you look at your R value, I have an R value of 0.883 for him. So the R value of 0.883, again, that's a pretty strong positive correlation. Okay, because we have a number pretty close to 1 there. Now, if your R value is something like, again, 0.5, 0.6, something like that, you might say you have a weak positive correlation. Let's look at the next question. It says, if you had guessed all of the ages correctly, what would be the equation of the line? Well, if I had guessed, or my husband had guessed, all of the equations, all of the ages correctly, that means whatever he guessed would also be the input and the output. So if he guessed, I don't know, 35 for someone, then the output would be 35, their actual age, or 40, 40, 50, 50. So all of our data values, the x's and the y's, the inputs and the outputs would look the same. So an equation of the line that would represent that would just be y equals x, meaning whatever my input was, x, my y would look exactly the same. What would the correlation coefficient be? Well, if I had all of my values that were correct, all of my x's and y's would be the same, that means that this equation, y equals x, would hit every single point. So my correlation coefficient would be exactly 1. As my guess went up, their age went up, or as their age went up, their guess went up. But again, we could draw a line that would connect all of those points. So the correlation coefficient would be a positive 1. In general, did you estimate or underestimate the ages, and how can you tell? So how can we tell? We can look at a picture of this. So we're going to hit y equals, and we're going to put our equation in there. Let me get rid of all of these that are in there already. There we go. And if I have 0.883x plus 4.725. So that's the line that would represent my husband's guesses. I'm also going to graph along with that this equation y equals x, which would be the equation if we had guessed every single thing correctly. So what I want you to be putting in your calculator is your equation for the line of best fit, and then in the second y equals x. Once you have them in there, make sure you hit zoom and then 9 to zoom in on this particular set of statistics. So let's see what we've got here. The blue line, I believe, was the first one. Yes, the blue line is the line that represents my husband's guesses. The red line represents if we had guessed every single one correctly. And you can see it looks like his is pretty darn close. At the lower values, he guessed a little high, and at the higher values, he guessed a little bit low. So as the person got older, he guessed a little bit under, and the younger people, he guessed a little bit older. Yours may look a little bit different. Maybe your blue line is well above the red line, and that means in general you guessed high. Or if your blue line's below your red line, that means in general you guessed low. His is a little mix of both. So did you overestimate or underestimate? He did both, and the picture is how we can tell. The graph of both lines, y equals x, the one that would have been correct, and then his guesses. Okay, so let's answer a question now. We want to know if the person's actual age was 37, what would have been the estimated age? So if their actual age was 37, remember those were our inputs, our x's. So we're going to type in y equals 0.883x, so 37, plus 4.725. And let's see how close he would have guessed. 0.883 times 37 plus 4.725. And he would have guessed pretty closely if they were 37 years old. He would have guessed 37.396. So if we were rounding that to the nearest whole number, he would have guessed correctly. So pretty good. Again, yours might look a little bit different than that. That was an interpolation problem because 37 is between ages that we were given in our table. The next question is we want to extrapolate. We want to say if somebody's age was 80, what would have been the actual age based on their model. So again, that's an input, an x value. And remember we said a few minutes ago, we thought that as the person got older, it looked like he kind of underestimated their age. So let's see if that shows up when I type in this value, 0.883 times 80 plus 4.725. And that's exactly what this shows. It says it's 75.365. So he would have guessed younger than 80. And finally, based on your age, what is your estimated age? So I'll tell you that my age is pretty close to 37, so I won't fill mine in here. You can do that as well on your own. You can type in your age and you can figure out what would then be the estimated age or the guessed age for you. So you can do that one for fun.